The normal mode simulation is an interactive educational tool designed to help students understand the fundamental concepts of normal modes in oscillating systems. This simulation provides a hands on approach to exploring the frequency, amplitude, and phase of normal modes, as well as the reasons behind the different frequencies of various modes. By engaging with the simulation, students can gain a deeper understanding of why higher numbered modes have higher frequencies and how to identify the number of normal modes in a given system. The frequency of a normal mode is the number of oscillations the system completes per unit of time, typically measured in hertz. Each normal mode has a unique frequency, which is determined by the physical properties of the system, such as its mass, stiffness, and boundary conditions. The frequency of a normal mode is a crucial parameter because it defines the rate at which the system oscillates. The amplitude of a normal mode refers to the maximum displacement of the system from its equilibrium position during the oscillation. The amplitude can vary depending on the initial conditions and the energy input into the system. In the context of normal modes, the amplitude is often used to describe the intensity or strength of the oscillation. The phase of a normal mode describes the relative timing of the oscillations of different parts of the system. In a normal mode, all parts of the system oscillate with a fixed phase relationship, meaning that they reach their maximum and minimum displacements at the same time. The phase is crucial for understanding the coordinated motion of the system. Normal modes are characterized by their unique frequencies, which arise from the system's physical properties and boundary conditions. The frequency of a normal mode is determined by the system's natural resonance, which depends on factors such as the mass distribution, stiffness, and the way the system is constrained. The mass and stiffness of the system play a significant role in determining the frequencies of the normal modes. Heavier systems tend to have lower frequencies because more mass requires more energy to oscillate. Conversely, stiffer systems have higher frequencies because the restoring force is stronger, causing the system to oscillate more rapidly. The boundary conditions of the system also influence the frequencies of the normal modes. For example, in a string fixed at both ends, the boundary conditions dictate that the ends of the string cannot move. This constraint leads to specific patterns of standing waves, each with a unique frequency. Normal modes are often numbered in ascending order of their frequencies. The fundamental mode, or the first normal mode, has the lowest frequency. Higher numbered modes have higher frequencies because they correspond to more complex patterns of oscillation. As the mode number increases, the pattern of oscillation becomes more complex. For example, in a vibrating string, the first normal mode corresponds to a single half-wavelength standing wave, while the second normal mode corresponds to a full wavelength, and so on. Higher numbered modes have more nodes, points of zero displacement, and antinodes, points of maximum displacement, leading to higher frequencies. Higher numbered modes require more energy to excite because they involve more complex patterns of motion. The additional energy is distributed across the system in a way that increases the frequency of the oscillation. This relationship between mode number and frequency is a fundamental property of oscillating systems. The number of normal modes a system has depends on its degrees of freedom, which is the number of independent ways the system can move. For a system with n degrees of freedom, there are n normal modes, degrees of freedom. In a simple system, such as a mass spring system, the number of degrees of freedom is equal to the number of masses. Each mass can oscillate independently, leading to a corresponding number of normal modes. In more complex systems, such as a vibrating plate or a molecule, the number of degrees of freedom can be much larger. The normal modes of these systems can be determined through mathematical analysis or computational methods, such as eigenvalue decomposition. The simulation allows students to adjust the parameters of the system, such as mass, stiffness, and boundary conditions, to observe how these changes affect the normal modes. By manipulating these parameters, students can gain a deeper understanding of the factors that influence the frequencies of normal modes. The simulation provides visual representations of the normal modes, allowing students to see the patterns of oscillation in real time. This visual approach helps students understand the relationships between different normal modes and their frequencies. Students can use the simulation to measure the frequency, amplitude, and phase of the normal modes. By observing these measurements, students can gain insights into the behavior of oscillating systems and the properties of normal modes. The simulation provides an interactive platform where students can actively engage with the concepts of normal modes. By manipulating the parameters of the system and observing the results, students can gain a deeper understanding of the relationships between different normal modes and their frequencies. The visual nature of the simulation makes abstract concepts more tangible. Students can observe the patterns of oscillation and the behavior of normal modes in real time, helping them to grasp complex ideas more easily. The simulation offers immediate feedback, allowing students to see the results of their adjustments instantly. This helps correct misunderstandings quickly and reinforces learning through trial and error. The simulation covers a wide range of topics related to normal modes, including frequency, amplitude, phase, and the factors that influence these properties. This comprehensive approach helps students gain a holistic understanding of normal modes and their applications in various fields. The normal mode simulation is a valuable tool for teaching and learning about the fundamental concepts of normal modes in oscillating systems. By providing an interactive, visual, and comprehensive platform, it helps students understand the frequency, amplitude, and phase of normal modes, as well as the reasons behind the different frequencies of various modes. Whether used in a classroom setting or for individual study, this simulation can significantly enhance the learning experience and build a strong foundation in the physics of oscillations and wave phenomena. Through exploration and experimentation, students can gain a deeper appreciation for the complex and fascinating world of normal modes and their applications in various fields.